Let's look at the solution to this system of equations right here. It's a very small system. It only has one equation in it. If we use linear algebra methods on this, we can write this as 1, 2, 3 augmented with 6. Right, because the 1 is the coefficient of the x, the 2 the coefficient of the y, the 3 the coefficient of the z. And this system of equations is already in reduced row echelon form. And what that tells us is that y is free. So y is free, it'll take on one of the parameters. And z is also free. So z will take on another parameter. And then if we were to plug these back into the original equation, we get x plus 2t plus 3s equals 6. And if we solve this for x, we get x is 6 minus 2t minus 3s, y is t, and z is s. So this gives us a parameterization for the solution to this system of equations. But we know that the original equation was a plane. So this parameterization right here must also be the same plane. So this gives the parameterization for the plane. If we think back to the equation of a line looked like AT plus x1, BT plus y1, CT plus z1, where the ABC was the direction vector and x1, y1, z1 was a point on the line. So this is an example of a space curve. It's a function that takes a real variable, in this case t, and gives us a vector in 3 space, gives us a point in space. So we call this a space curve. Space because the range is 3-dimensional, and curve because the domain is 1-dimensional. If we take the same idea, but now we have a function of 2 variables, where the first one is a function of s and t, the second component is a function of s and t, and the third component is a function of s and t. This is a function of 2 variables, and our output is a vector in 3 space. You can think of this as a space surface. It's in space because the range is 3-dimensional, and it's a surface because the domain is 2-dimensional, have these 2 independent parameters. So your book calls this space surface a parametrized surface. So we see we have an example right here of a parametrized surface. We can, if we were to change these functions, make them a little bit more complicated so they weren't just lines, we could add some curve to the surface. Let's see some examples of how you could parameterize surface. So let's say we want to get the equation that we have into parametric form. Well, first up, if we've got a function, this is the sort of easiest type. If z is a function of x and y, the easiest, most straightforward way to do this is, since z depends on x and y already, we can give x the value of one of the parameters, y the other parameter, and z will just be the original function of t and s. So this will be our parameterization for this surface right here. Really doesn't look like we did much on here. Let's look at an example of this. Say we have z is x squared plus sine of x minus y. Well, our parameterization would be x equals t, y equals s, and z equals t squared plus sine of t minus s. So if we have a function, if one of the variables is a function of the other two, getting it in parametric form is actually pretty easy. And z doesn't have to be the loner variable here. We could have just the same had y equals f of x and z, and this would give us a similar parameterization. X is free, z is free, and then y is the function of the other 2 variables. So that works similarly to the example we did right here. What about surfaces that aren't given one variable as a function of the other 2? Well, let's take a look at a cylinder first. So a cylinder is x squared plus y squared equals, say, 9, and there is no z coordinate, so z is free. Well, z is free, so that means z gets the value of one of the parameters. So now z is sort of out of the picture. Let's think of this circle right here. If we were to parameterize this, think to polar, we have that x is equal to 3 cosine t and y is equal to 3 sine t. And there's our parameterization. Z was free, so it was kind of independent of the other two. We could parameterize x and y on their own and then sort of tack the z on as an afterthought. Let's look at one that's a little bit more complicated, a sphere. So we've got the equation x squared plus y squared plus z squared is 4. Well, here we have no free variables. If you look at the previous problem, though, this looks like cylindrical coordinates, the way we've set this up. Z is sort of on its own, independent of the polar part, and x and y, we really just converted the polar. We can do the same thing here if we change to spherical. So recall x is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. Well, if we're on the sphere, then rho is fixed, or the radius of the sphere is 2, so I know rho is 2. If we look at phi and theta, though, we've got to be able to take on any point on the entire sphere. That means that phi, remember this is the angle of depression from the North Pole, so phi can range from 0 to pi, and theta is the angle around the North Pole. This can take on its full range of values from 0 to 2 pi. So you can kind of think of these as being free. These can take on any value, whereas the rho is fixed. So if we were to write our parameterization, we'll just take the formulas that we have for spherical and fill in what we know. The rho is 2. The phi is free, so we may as well call that one of the variables. And the theta is also free, so we can call that the other variable. And then we'll just fill them in. So sine of t, sine of s, and the z is 2 cosine t. And that gives us our parameterization for a sphere. Now that we've got some of these surfaces out of the way, let's look at how we do calculus in terms of these parametric forms. So the first thing we're going to look at is the normal vector. This is sort of the derivative operator, if you will, on the surface. So if we look at the normal vector, r is a function of two variables, and it has three components. It has the x component, it has a y component, and it has a z component. Now if we want to look at the normal vector here, well, remember the normal vectors to a surface, we can think of this if we've got two tangent vectors to the surface. If we've got a tangent vector and another tangent vector, it has to be perpendicular to both tangent vectors, and that's just the cross product. We know the cross will give us a vector perpendicular to two vectors to begin with. So if we want to get if we're looking for two different tangent vectors here, one thing that we can do is we can look at the partial derivatives of this with respect to each of the two variables. So we can think of this like the partial of r with respect to s, and the second tangent vector is the partial of r with respect to t. We go and cross these two and we've got our normal vector. Let's look at an example of this in action. Let's actually take something that we can do, we can check as a function. Let's say z is x squared plus y squared. So we know that our parameterization for this will be x is free, y is free, and z is t squared plus s squared. So there's our parameterization. Let's look at our two tangent vectors going in. t1, well, that will be the partial of this vector here with respect to s. Well, the partial of x with respect to s is 0. The partial of y with respect to s is 1. The partial of z with respect to s is 2s. If we look at our second tangent vector, this is the one running in the t direction, we take our partials with respect to t. The partial of x with respect to t is 1. The partial of y with respect to t is 0. The partial of z with respect to t is 2t. And now I'll cross these two. So our normal vector will be the determinant of this matrix, I, J, K. The first row, or the second row, is the entry of our first vector, and our bottom row is the entries of our second vector. Now if we cross these, we've got in the I component, on the I component we've got this multiplication right here, 1 times 2t minus 2s times 0, so that's just 2t. In the minus j component we've got 0 subtract 2s times 1, so negative 2s. And then in the k component we've got this multiplication right here, which is 0 subtract 1, so negative 1. So if we write this out, this is the vector 2t, 2s, negative 1. Now how can we check to make sure that this is correct? Well, if we look at what the original parameterization was, t was x, s was y. So if we were to plug this, sort of do this reverse parametric, if we eliminate the parameters here, this gives us 2x, 2y, negative 1. Well, if we look at the method that we had before parametrizing surfaces, what we would do is take the gradient of that surface. So if we take the gradient of this, this is x squared plus y squared minus z. This gives us as our normal vector, partial with respect to x, and then partial with respect to y, and then partial with respect to z. So this checks. This just gives us a way to, an alternative way of finding the tangent vector. And in some surfaces, taking the gradient straight up may be a lot more complicated than parametrizing. So the second part we have on this for calculus on these parametric surfaces is arc length. So for arc length, we're not going to actually go through this. We'll just do an example of how you set up an arc length. Your arc length is going to be the double integral over whatever your region is of the partial of r with respect to s cross the partial of r with respect to t. And because we're taking the magnitude of this is with respect to area, because we're taking the magnitude of this, it really doesn't matter which partial derivative you take first, whether you decided to take t or s. Because we have the magnitude in there, that'll take care of it. So let's look at an example. Let's actually take the same surface we had, this z equals x squared plus y squared. Z equals x squared plus y squared over the unit disk. So we've got our parameterization already. This is the thing that we actually just figured out in the previous step. So our arc length here, or not arc length, this is surface area, because we have a surface, not a line or an arc. So the surface area formula is given by this double integral. So the surface area is given by the double integral over the region, which in this case is the unit disk, of, well, we want to take our two tangent vectors, dr ds and dr dt, and we'd actually figured those out in the previous step, t1 and t2. So 0, 1, 2s, 0, 1, 2s, cross 0, 1, 2t with respect to area. And furthermore, if we look back, we've actually done this cross product in the previous step. That was actually the normal vector. And what we had for that was double integral over r.